Rotations are everywhere in robotics, from pose estimation to motion planning and calibration. Today we'll build them from the ground up, starting in 2D and then stepping into 3D. Most of you should be familiar with how to change the position of a vector. We simply add a second vector and the sum of them gives us a new one. But how do we rotate a vector? For this we use a so-called rotation matrix. Here you can see the rotation matrix for 2D rotations. If we want to rotate our vector by 90 degrees, for example, we simply plug in the radians, so pi over 2, in the rotation matrix and do a simple matrix vector multiplication. The product is the new rotated vector. It is to mention that the rotation is always counterclockwise, even later on in 3D space. Now, where do the entries of the rotation matrix come from? For this, we take a closer look at the unit circle. The vectors x and y are the base of our 2D space, and we can construct every vector from a combination of these two. Let's see what happens when we turn them by an unknown angle theta. From simple trigonometry, we can see that the y component of x is sine of theta. We can also see that the x component of x is cosine of theta. For the y vector, it's almost the same. The x component is negative sine of theta, and the y component is cosine of theta. If we put the vectors side by side like this, we can see that the entries match our rotation matrix. Moving up to 3D space, nothing really changes. We just have an additional dimension. But as you can see, the row and the column of the axis we rotate around remains the same as in the identity matrix, and the remaining entries are just the same as in the 2D rotation matrix. Now most of the time rotations are not just around one axis, so let's see how we combine them. Let's say we want a 25-degree rotation around the x-axis and then a 70-degree rotation around the z-axis. For this, we simply take the rotation matrix of the x-axis, multiply it by the rotation of the matrix for the z-axis, and we get our combined rotation matrix. But here's the crucial part: the order matters. Matrix multiplication is not commutative, which means Rx times Rz is not the same as Rz times Rx, as you can see here. This brings us to standard conventions for combining rotations. The most common are the Euler angles and the Tait-Bryan angles. Euler angles use 3 rotations where the first and the third rotation are around the same axis, like x, y, x. These are popular in aerospace and physics because they avoid certain mathematical singularities. Tait-Bryan angles, on the other hand, use 3 rotations around 3 different axes, like x, y, z. These are more intuitive and commonly used in robotics. You might know them as roll, pitch, and yaw. Here you can see all possible combinations of both conventions. Now there are 2 ways to interpret these rotation sequences: extrinsic and intrinsic rotations. Extrinsic rotations happen around fixed world axes. If we do an extrinsic x, y, z sequence, we rotate around the world's x-axis, then the world's y-axis, and then the world's z-axis. The axes don't move. The matrix multiplication is Rz times Ry times Rx, where the rightmost matrix is applied first. Intrinsic rotations happen around the object's own axis. With each rotation, the object's coordinate frame moves, so rotations happen around the object's new rotated axis. Rotated axes are often marked with an apostrophe, and double rotated axes are marked with 2 apostrophes. For an intrinsic xyz rotation, the matrix multiplication is Rx times Ry times Rz, where we multiply in the same order as the rotation sequence. If we go back here, every combination can be viewed as extrinsic or intrinsic, doubling the amount of possible conventions. The takeaway here is to always know which convention you're using and whether you're working with intrinsic or extrinsic rotations. And that's it for rotation matrices. If this helped you understand them better, hit that like button, and if you have any questions or topics you'd like to see next, drop them in the comments below. Thanks for watching, and I'll see you in the next one.